I think it's about time. So welcome everyone to this afternoon's session of the European Non-Associative Algebra seminar. Today's talk will be given by Saikat Goswami from the Institute for Advancing Intelligence in India on the topic of universal constructions on algebras over operads. So over to you, Saikat.
Thank you so much. Am I audible?
Yes.
Okay. Thanks to the organizer for inviting me to give a talk at the European Non-Associative Algebra seminar. And okay, so I begin my talk.
Yes, please do.
Okay. So I will share my screen. Is the screen visible?
Yes, it's visible to me.
Okay, thank you. So today's talk, I want to present our work that I have done with my collaborators, Shotendra Kumar Mishra and Shuman Patnaik. So this is a work which deals with algebras over operads and some constructions on these algebras. So at first, I would like to give the background and motivation of our work, and then some preliminaries that we will need to introduce our work. So I will start with the introduction. So if A is an associative, unital associative algebra over a field K, in 1968, Swidler showed that the Hopf functor has a right adjoint, and the algebra MA turns out to be a bialgebra and is the final object in the category of all bialgebras that act on A, making it a MA module. In 1988, Manin and Tambara addressed the dual version of the above statement. So more precisely, they proved the following. So if A is finite dimensional, unital associative algebra, then the tensor functor admits a left adjoint and is denoted by CA. CA is further shown to be a bialgebra and is the initial object in the category of all bialgebras that coact on A, making it a CA comodule. Then in 2020, Agore and Militaru studied the tensor product functor in the category of Lie and Leibniz algebras, Poisson algebras, and some other kinds of algebras like omega algebras and things like that. More precisely, if they showed that if G is a Leibniz algebra and A is a commutative algebra, then there exists a Leibniz algebra structure on the tensor product, and the Leibniz algebra structure on the vector space G tensor A is defined this way. So they pull out the commutative part and keep the Leibniz algebra part on the left and the commutative part on the right. And they showed that for any Leibniz algebra G, the tensor functor admits a left adjoint if and only if G is finite dimensional. Our motivation was to generalize the work of Agore to the category of all P algebras, where P is considered to be an arbitrary symmetric operad. So what we found is that if we start with an arbitrary symmetric operad and take A to be an algebra over the operad P, then there exists a tensor product functor coming from A, from the category of all commutative algebras to the category of all P algebras. And the tensor product functor admits a left adjoint if and only if A is considered to be finite dimensional. We also showed that the category of all finite dimensional P algebra is enriched over the opposite category of commutative algebras. As a consequence, we showed that CA turns out to be a bialgebra. And finally, this functor, the adjoint functor construction, helped us to characterize the automorphism group of A and to characterize all possible abelian group gradings of A following the works of Agore and Militaru. So this was the background and the motivation for our work. I will start with describing what we mean by an operad, and once I have introduced all the necessary things I need to describe our results, I will start with describing our work. So what are operads? So the notion of operads appeared in J.P. May's work in 1970 in the work named The Geometry of Iterated Loop Spaces. So the word operad is somehow a contraction of two words, operation and monad. So the basic intuition is like, so by an operad, it is, it's a sequence of sets with a composition function, an action of a symmetric group on each Pn, a unit in P1 which satisfies some compatibility conditions. Sometimes the set Pn contains some richer structures, such as vector spaces, topological spaces. There are also 10 complexes, simplicial sets, many more. So a toy model for operad. Before giving the abstract definition of operad, I would give a small example, and then I would introduce the definition of operads. So for any set X, if we consider the sequence of sets, like all set maps from Xn to X, where Xn, I mean the Cartesian product of sets. So each element of this particular set, map Xn X, can be seen as a corolla. And for any I varying from 1 to n, we define the composition map as follows. So we just replace the ith entry of f with another function g, and this is how the ith composition looks like. So the output of g is inserted as the ith input of f. And the composition map satisfies the following associativity condition, where the dash present below the circles are suitable choices of I and j. So you can see that there are many places. So suppose I want to, after composing f with g, I want to put another h. So there are three places of putting an h. One is at the top of G here, the other is at the left side of G here, and the other is at the right side of G here. This gives us, depending on the choice of I and J, we have a partition of J. So J can vary from I to 1 to I minus 1. That would give us the first associativity condition. J then would vary from I to I plus Q minus 1. That means the H is sitting on top of G. And that gives us this associativity condition, this following associativity condition. And J can be vary from I plus Q to P plus Q minus 1. That means that the tree H can sit on the right of G. And that gives us this particular associativity condition. So this is what the associativity condition for operad looks like. And there is also a SN action, like I said before. And the SN action is defined this way. So given a map F sigma on S1 up to Xn is defined this way. So it permutes it acts on the position of the elements of X1 up to Xn, on the variables, position of the variables. So for any F and G, the action satisfies the following equivariance condition, where sigma circle I tau is the block permutation, where ith entry of sigma is replaced by the entire block of tau. With this motivation, I give the complete definition of what we mean by an operad. So an operad in the category of vector spaces is a sequence of K vector space P together with linear maps, which are basically composition maps, which satisfies the associativity axiom, which we saw just a few slides ago. Then the equivariance axiom. So there exists the right action of Sn on Pn for each n, which satisfies the following the compatibility condition with the circle product, and the unit axiom. That means there exists a unit element in P1 such that for all f belong to Pn, we have this condition. This was one possible definition of operad. There are many other equivalent definitions of operad, such as the classical definition or the monoidal definition. I would give the monoidal definition, but this is the most economic way of saying, efficient way of saying what an operad is. So for that, we need S modules. So an S module is a family of K vector spaces equipped with the right action of Sn. And the monoidal product of two S module is defined this way. So M circle N is again a S module where the nth component of M circle N is given this way. So this Mk represents a corolla, and each of Ni up to Nik are another corolla sitting on each input of the corolla coming from Mk. And an algebraic operad is a monoid in the monoidal category of S modules. Sometimes we also see operad as a functor from the category of as an endofunctor in the category of vector spaces, and it is defined this way. So any given operad P and a vector space V, PV is defined as Pn tensor V tensor n, and the sum is taken over all n. This gives us the monoidal definition of operads. Now we'll see some examples of operads. And the most important and the prototypical example is called the endomorphism operad. So we start with a vector space V. The endomorphism operad over V is defined as follows. So NV of n is, instead of taking set maps, now we take linear maps from V tensor n to V. And the symmetric group action is defined similarly as in the case of map Xnx. And the identity map serves as the unit of the operad. So we will need this to define the notion of algebras over operads, that which we denoted by P-alg. So a morphism between two operad consists of sequence of linear maps Pn to Qn, such that the 2 diagram is commutative. And an algebra over an operad P is so by that I mean a vector space A is said to be an algebra over an operad given operad P if there exists a morphism of operad from P to end A. Now we'll see some example. So the question is, what is the operad such that algebras over it are precisely commutative, associative, non-unital algebras? So the operad com is defined as follows, where P com n is we take 0 to when n is 0, and for n greater or equals to 1, we take k, where the partial composition is given by you take any element from com n, which is k, you take any element from com m, which is k, and you define the ith composition as the multiplication coming from the base field k, which is defined as AB. And the Sn action is given by the trivial action. So this is an operad, and any algebra over this operad are precisely commutative, associative, non-unital algebras. Similarly, the operad as is defined as follows. For n equal to 1, we have k. For n greater or equal to 2, we have ksn. As n is ksn. And the partial composition is defined using the block permutation on Sn, and the as n is induces the as n, the partial composition is coming from the group multiplication of Sn. So any algebra over the operad as is precisely associative non-unital algebra. Now we will see the description of the operad Lie. This encodes the category of all Lie algebras, where Lie n is generated by formal expressions obtained by bracketing n many symbols, x1 up to xn, in such a way that each symbols appear exactly once, and the smallest index inside the bracket on the left hand are present on the left hand side, and the largest index appears on the right hand side. So an example is like this. So x1, x2, bracket x3 is in Lie 3, but x2, x1, x3 is not an element of Lie 3. So to each element of Lie n, we can associate a decorated planar binary tree, and for n equal to 2 and 3, the vector space generators of Lie 2 and Lie 3 are described as follows. Similarly, some basis elements of I have not listed all the basis elements of LD4. I have just described to get an understanding of how it looks like. I have stated down 3 elements. Now we'll see a functor which is called the tensor functor from the category of commutative algebras to the category of P algebras. So for any fixed P algebra A with structure map gamma, the tensor functor is defined as follows. So we start with the commutative algebra C. The P algebra structure on A tensor C is denoted by this equation, which is similar to the case of Lie algebras. Here in Lie algebra, we put the Lie bracket on the left-hand side and the commutative part on the right-hand side of the tensor product. Similarly, here also we do the P algebra structure comes from gamma, which is on the left-hand side of the tensor product, and the commutative part is put on the right-hand side of the tensor product. This gives us a functor from the category of commutative algebras to the category of P algebras. Now the question is, do this functor admits a left adjoint? So in the case of Lie, Leibniz, and Poisson, it was answered by Agore's work, and in our work, we extend this construction to the category of all P algebras. So the main theorem of our work is if we start with an operad P and fix an algebra over this operad P, then the following results hold. The tensor functor from commutative algebra to P algebra admits a left adjoint if and only if A is finite dimensional. This generalizes the result obtained for Lie-Leibniz algebras, Poisson algebras, Lie-Yamaguchi algebras to algebras over operads. So this result is also true in the category of, for example, Jinville algebras, pre-Lie algebras, Garsten-Ebor algebras, and many more. So now I would like to describe the construction of this functor CA from P algebra to commutative algebra. So I start with a P algebra B, and the aim is to construct a commutative algebra CAB. So we start with a linear basis of A and a linear basis of B. And B, since B is an arbitrary element of the P algebra, so it did not be a finite dimensional algebra. So here, when taking a linear basis of B, we are taking it to be indexed by indexing set I. So then for any mu in Pk, we obtain the following structure constants, where gamma A denotes the P algebra structure of A, and gamma B denotes the P algebra structure of B. And we define CAB to be a quotient of the polynomial algebra over the variables coming from XSI, where S runs from 1 to n. This corresponds to the n corresponds to the dimension of A, and I corresponds to the indexing set of the linear basis of B, where the ideal J in CAB is generated by polynomials of the following form. Now we will see why we need this, why we need to quotient with these polynomials. So before understanding why do we need to quotient the polynomial by the ideal J, we just fix some notations. We denote by XSI the class XSI in the algebra CAB. So as of now, to any algebra P algebra B, we have associated a commutative algebra CAB as which is defined as the quotient algebra of the polynomial algebra. Now we need to see how morphisms in P algebra corresponds to morphisms in commutative algebra. And to make this correspondence, we start by defining a linear map, eta B, defined as follows. Then, to show that this map eta B is a P algebra morphism, we need the polynomial identities present in J. This polynomial identities in J would give us the commutativity of this diagram, which basically tells us that the map eta B is a P algebra morphism. And using the P algebra morphism eta B, we obtain a correspondence between P algebra morphisms and commutative algebra morphisms. This gives us the functor CA from P algebra to commutative algebra. So, and the commutative algebra CAB satisfies the following universal property, that if we take any commutative algebra C and a P algebra morphism from B to A tensor C, then there exists a commutative algebra morphism from CAB to C, thus that this diagram commutes. So as a result, we have the following bijection from CAB all between the set of all morphisms from CAB to C and P algebra morphisms from B to A tensor C. And this gives us the desired adjunction between the two functors, the tensor product functor and the functor which we constructed, which is CA. Now, we would like to give a basis-free description for the functor CA. So if I start with P algebra B, then we consider the free non-unital commutative algebra over the vector space B tensor A sharp. By A sharp, I mean the dual of the linear dual of A, and we define a map alpha from B to A tensor the commutative algebra as follows. So I identify B with B tensor K, and then I take the co-evaluation map from which takes us to B tensor A sharp, and then using the twist map and the inclusion map, we get a map from B to A tensor, the commutative algebra, which is the symmetrical non-unital symmetric algebra over the vector space B tensor A sharp. Then the map alpha will induce a map from PB to P of A tensor A star. And this map will induce, along with the structure maps PB to B, will induce two linear maps, alpha 1 and alpha 2, which is like PB to A tensor the symmetric algebra and PB to A tensor the symmetric algebra over B tensor A sharp. And since A is finite dimensional, the linear maps alpha 1 and alpha 2 corresponds to two linear maps where I can pull A to this side and get these two maps. And J is precisely the J we described earlier using polynomials is precisely the ideal generated by the image of phi 1 minus phi 2. And we define CAB to be the symmetric algebra quotient out by J. So this gives us a basis-free description of the functor we constructed. And now we show that this particular category is enriched over the category of commutative algebras using the functor we constructed in this section. So at first I recall the definition of an enriched category. So let M be a monoidal category. A category enriched over M is a category C consisting of the following data: a class of objects which is called OBC, and for any pair of objects A and B in the enriched category, there exists MAB, which is called the home object of M A and B, which is an object in M. And for any arrow between A and B in the enriched category, it is basically given by a morphism from the initial object to the home object MAB. And for any object A, B, and C, there exists a composition morphism, which is denoted by circle ABC. And for each object, there is a morphism eta A, which is known as the identity morphism. With this definition, we show that the category of all finite dimensional P algebra is enriched over the category of opposite category of commutative algebras. So if we start with two finite dimensional P algebra, we take the home object to be CBA. And for any A in P, any finite dimensional P algebra, the universality of CA determines a map eta A from CA to K. So here K is considered as a commutative algebra. This eta A serves as the identity morphism. And for any ABC, if we consider CAB tensor CBC, and we take the map F to be eta CB, which takes us from C to B tensor CBC, and then again applying eta BA to B, we get a map from B to A tensor CAB. This map is a P algebra morphism. So that using the universality of A and CAC, we get a map triangle ABC, and we define the composition morphism ABC as triangle CBA, the opposite of in the opposite category. So that this gives us an enrichment of the category of a finite dimensional P algebra over the commutative algebra. Now, in the above diagram, if we take A, B, and C to be equal, then we get a unique morphism from CAA to CA, tensor CA, which gives us a bialgebra structure on CA. Now, as an application, we characterize the automorphism group of a given P algebra, finite dimensional P algebra. So if we start with a finite dimensional P algebra A and the universal coacting bialgebra CA, we denote the set of all group-like elements of CA to be C, such that triangle of C is the co-multiplication of C is given by C tensor C. This is a monoid with respect to the multiplication of CA. And then we take CA dual, CA circle, denote the finite dual bialgebra of CA. We recall that all the group-like elements of this finite dual bialgebra is in equality with all possible algebra maps from CA to K. And finally, we denote by this the group of all invertible group-like elements of CA circle. And the theorem is the following. For any A finite dimensional P algebra A, there exists an isomorphism of group. So this isomorphism comes from the following adjunction we showed earlier. So using the adjunction, we have the following bijection between the P algebra maps from AA and the commutative algebra morphisms from CA to K, which is the same as all the set of all group-like elements over CA star. This gives us an isomorphism of monoids, and restricting it to the set of all invertible elements gives us the required isomorphism gamma. So in this way, we can describe the automorphism group of a finite dimensional P algebra. And then we show the classification of all abelian group gradings of a given finite dimensional P algebra. So let A be a finite dimensional P algebra and G be an abelian group. A G grading on A is a linear decomposition of this form such that the following condition holds. So this basically means that if I take elements G1 up to Gk from this from the corresponding composition from the corresponding factors, if I multiply them, I end up getting an element in A G1 up to Gk for any mu belonging to Pk. This tells that there exists a bijection between the set of all G linear decompositions of A and the set of all right Kg co-module structures on F on A. And this co-module structure F is a P algebra morphism if and only if it gives a linear decomposition on A. So thus, the set of all G gradings on the P algebra A is in bijection with the set of all P algebra morphisms from A to A tensor, the group algebra Kg, such that A turns out to be a right Kg comodule. And the universal property of the bialgebra gives us a bijection between the above set and all bialgebra maps from Ca to Kg. This gives us the theorem that if A is a finite dimensional P algebra and G is an abelian group, there exists a bijection between the set of all G gradings of A and all bialgebra morphisms from Ca to Kg. This is the references I used to prepare this talk. And, thank you.
Okay, thank you very much. Certainly managed to get through that in double quick time. Are there any questions or comments that anyone would like to make? No? Okay, well, can we thank Saikat again for a very interesting talk. So thank you.
Thank you.